Right now, this very second, you are perfectly still. Maybe you're sitting in a chair. The air in the room is calm. The table doesn't even tremble. But that's the grandest illusion in human history. At this exact instant, your body rips through empty space at speeds many times the speed of sound. This isn't a metaphor. Right now, you outpace a sniper's bullet as it leaves the barrel. You overtake a fighter jet on full afterburner. You're a passenger on a planetary bolide, riding its eternal, silent, furious passage through the cosmic abyss. And you feel none of it. Stillness is a lie. Comfortable, familiar, and utterly false. We trust our senses, yet they mislead us about the biggest thing, our place in the universe. That illusion of rest runs so deep that it took humanity thousands of years, bloody sacrifices and flashes of genius to shatter it. We'll unpack just how vast our motion really is. We'll look back and see the terrible price paid by those who first dared to say, and yet, it moves. We'll understand why whole civilizations clung to the idea of a motionless Earth for centuries. And we'll confront the central paradox. How do you prove the Earth is turning without looking at the stars? How, locked inside a sealed room, do you figure out your world is a giant spinning top? The answer to that question transformed science and opened the door to understanding the universe's deepest laws, from the birth of stars to the very nature of matter. Let's take this illusion apart. Start small. If you're standing on the equator, you're whipping around with the planet at about 460 meters per second. The speed of sound in air is roughly 343 meters per second. You're moving faster than sound just by standing still. But that's only the first rung of the cosmic race. Earth doesn't just spin. It also streaks around the sun at about 30 kilometers per second. That's not just a statistic. In 1 second, while you blink, Earth barrels through space a distance equal to 3 of its own diameters. In the few minutes you'll spend watching this video, we'll sail thousands of kilometers. It's like crossing an entire continent while the kettle comes to a boil. The sun, our giant thermonuclear furnace, pulls its whole entourage of planets, asteroids, and comets along through interstellar space. And that colossal convoy moves at about 220 kilometers per second. Every second. 220 kilometers. That's like going from New York City to Philadelphia in a single heartbeat. How do you measure time when the stage is an entire galaxy? To grasp this scale, we have to trade our familiar hours and years for something larger, the galactic year. That's the time it takes our solar system to make one full circuit around the center of the Milky Way. It lasts about 230 million Earth years. Think about that. The last time our system sat in this same spot along its galactic orbit, dinosaurs ruled the planet. Triceratops and Tyrannosaurus roamed a world that occupied the very same patch of the galaxy we occupy today. In the whole history of complex multicellular life on Earth, we have not even completed 3 full orbits. All of human civilization, from building the pyramids to launching spacecraft, fits into a tiny, almost invisible sliver of that galactic path. We are a speck of dust aboard a spaceship, racing along an orbit that stretches for hundreds of thousands of light years. And our journey is only beginning. Now it's clear why the illusion of stillness felt so convincing. Why our ancestors, staring up at the sky, were absolutely certain they stood still. Their reasoning made perfect sense, rooted in what they could see. The sun rises in the east, crosses the sky, and sets in the west. The moon and the stars do the same. The ground beneath your feet feels solid and unmoving. Jump and you land in the same spot. So the logic followed. If Earth were rushing through space at some enormous speed, then when we jumped, we'd fall behind. The planet would slip out from under us. Wind would sweep everything off the surface. Oceans would spill into space. That feeling of stillness is a basic human experience. And that experience shouted one thing. We are the center of everything. The universe revolves around us. That intuitive certainty gave rise to one of the most enduring and elegant scientific theories in history, Ptolemy's geocentric model. Don't dismiss it as a crude guess. It was the pinnacle of ancient mathematics and astronomy. In the 2nd century, Ptolemy built an extraordinarily intricate system that did more than describe planetary motion. It predicted it with striking accuracy. Planets didn't move on simple circles. They traced epicycles, small circles whose centers, in turn, traveled along larger circles called deferents. It looked like a celestial clockwork of astonishing complexity. And it worked. Astronomers used Ptolemy's model to calculate planetary positions years in advance and to predict eclipses. The system delivered answers. It had mathematical beauty. Most important, it confirmed what people felt intuitively. The Earth stood motionless at the center of the cosmos. That doctrine endured for nearly 14 centuries. 14 centuries of intellectual stagnation, reinforced by the Church's authority. In the 16th century, Nicholas Copernicus, a Polish church canon, physician, and astronomer, quietly launched a revolution. Working with the same observations as everyone else, he saw what no one else did. He realized that if you swap the positions of Earth and the Sun, put our star at the center, the clumsy Ptolemaic system with its epicycles simply falls apart. The model becomes cleaner, more logical, more elegant. Planets begin to travel on simple circular orbits. Those strange loops Mars and Jupiter traced across the sky weren't the planet's own complicated dances. They were a trick of perspective, the result of watching them from a moving platform. Earth. It was a breakthrough with enormous consequences. But Copernicus wasn't a daredevil. He was a careful scientist, and he was afraid. He understood his discovery wasn't just a tweak to the star charts. It struck at the foundations of how people understood the world. It toppled humanity from the center of the universe. For decades, he put off publishing his book On the Revolutions of the Celestial Spheres, fearing his colleagues' ridicule and the Church's wrath. He didn't see it in print until he lay on his deathbed. He had achieved a monumental intellectual feat, but he never lived to see the storm he had set in motion. If Copernicus planted a bomb under the old worldview, others paid with their lives to set it off. Giordano Bruno, philosopher and poet, pushed Copernicus further. He didn't just accept the heliocentric model. He traced its philosophical consequences. If Earth is only one planet orbiting one star, why couldn't other stars be suns too? Why couldn't they have planets of their own with other forms of life? The Inquisition put him on trial for those ideas, for his belief in an infinite universe and the existence of many worlds. After 8 years of imprisonment, torture, and interrogation, he refused to recant. In 1600, the authorities burned him alive on the Campo dei Fiori, Rome's flower square. His execution became a chilling symbol of how dogma silences free thought. Just a few decades later, Galileo Galilei found himself on trial. Unlike Giordano Bruno, Galileo didn't just have bold ideas, he had evidence. He pointed a telescope at the heavens and watched the Ptolemaic model fall apart. Mountains on the moon, phases of Venus that mirrored the moons, and above all 4 moons orbiting Jupiter. That was tangible proof that some celestial bodies did not circle the Earth. It was a verdict on the old cosmic order. But the establishment would not relent. They forced the 70-year-old, ailing Galileo to kneel in public and renounce his beliefs. He saved his life but spent the rest of his days under house arrest. People had seen the truth, yet the price they paid for it was unbearably high. Here's the central paradox. Copernicus, Bruno, Galileo, all those great minds, proved the Earth moves by looking at the sky. Their arguments rested on the motion of the planets, the stars, and Jupiter's moons. They looked outward to understand what was happening under their feet. And yet, for centuries, there was no way to prove the Earth was rotating while standing on it, without ever looking into space. That was the weak spot in their case. A skeptic could always say, "Your math is complicated, and a telescope can deceive. I'm standing on solid ground and I feel no motion." How could you prove them wrong? What simple visible phenomenon here on Earth could silently show that our planet is, in fact, a giant spinning top hurtling through space? For 2 centuries, Galileo and Newton chased an answer that turned out to be laughably simple. No telescopes, no complex equations, just a wire and a heavy ball. In 1851, French physicist Léon Foucault gave the world not a theory but a spectacle. He built the first direct, irrefutable, and most importantly, visually obvious proof that the planet rotates. Anyone could see and understand it, from academics to ordinary workers. Foucault didn't show the motion of the heavens. He made the Earth itself give up its secret, the Paris Pantheon, a vast, echoing, cold cathedral of science, mausoleum of France's greats. Under its colossal dome, a crowd gathered, not professors at a lecture, but everyday citizens, journalists, skeptics, dreamers. Tension filled the air, a mixture of reverence and doubt. From the dome's highest point hung a thin steel cable 67 meters long, the height of a 20-story building. At its end, a massive brass sphere hung nearly touching the floor. It weighed 28 kilograms. A circle had been traced on the floor and dusted with sand. Foucault gently pulled the ball aside and tied it with a string. Then he burned through the string. No push, no jolt. The pendulum began its slow, majestic, and utterly silent swing. Forward and back, forward and back. At first, nothing happened. The crowd watched, holding its breath. The ball swung smoothly in a single plane, carving a thin groove in the sand. Minutes dragged on. Then the most observant began to notice something strange. Incredible. The next groove did not fall exactly on top of the first. It was shifted, slightly by millimeters. But the plane had shifted clockwise. The pendulum kept swinging, steady and hypnotic. With each arc, its plane turned a little more, slowly, inexorably. It looked as if some invisible hand were twisting it. That was Foucault's genius. There was no hidden force. The pendulum's plane stayed absolutely fixed against the distant stars. It was an anchor cast into still space. It wasn't the pendulum that turned, it was the floor of the Pantheon. The city of Paris, the whole continent. The entire planet, Earth itself, was rotating slowly beneath it. The hall fell silent. Then a low murmur of astonishment rose. For the first time, people saw it with their own eyes, not on diagrams, not in calculations, but live. They watched a silent dance with their own world as the partner. It was more than an experiment. It felt like a philosophical revolution happening in real time. For centuries, people trusted their senses. Senses that insisted the world stood still. Then a simple metal ball on a cord, silent and elegant, exposed those senses as clever deceivers. Foucault's genius was to make Earth's rotation a personal experience for anyone who watched his pendulum. A doctrine that had stood for millennia collapsed beneath the steady arc of the swinging bob. The idea of a motionless Earth vanished. The pendulum answered the what. It showed that Earth rotates. But it left a deeper question hanging. Why? Why does anything in the universe spin at all? Why do planets, stars, even whole galaxies refuse to drift motionless, instead joining this vast cosmic dance? Where did that first push come from? That invisible engine that, billions of years ago, set the whole mechanism in motion and still won't let it stop? The answer isn't in astronomy. It lives in one of the most elegant laws of physics. The same rule that governs a child's spinning top and giant black holes. You don't have to travel to space to see it. Just go to an ice rink. A skater begins her spin slowly, arms spread wide. Her motion is graceful, deliberate. Then the trick happens. She snaps her arms in tight. In the same instant, her spin rate explodes. She blurs into a human top. She didn't shove off the ice, nobody pushed her. Where did that sudden surge of energy come from? It didn't come from nowhere. It was always there, hiding in the slow, wide sweep of her outstretched arms as she turned. That's conservation of angular momentum at work. Angular momentum is roughly the amount of spin an object carries. And in the universe, that amount stays constant unless something from the outside applies a force. When a skater stretches her arms out, most of her mass sits far from the axis of rotation. To keep the same total spin, she has to rotate more slowly. But when she pulls her arms in, drawing mass toward the axis, the system has to compensate. The only way to do that is to spin up, faster and faster. A smaller radius demands a higher spin to preserve the same angular momentum. Now swap the skater for a giant cloud of interstellar gas and her arms for trillions of tons of dust and hydrogen. Now bring in one relentless force. Gravity. It always pulls. It always squeezes. Think of gravity as a cosmic coach. The kind that forces a skater to tuck her arms in tight. It draws that diffuse, gigantic cloud inward toward its center. The same rule applies here. At first, this cloud, stretching across light years, carried a tiny, almost imperceptible spin. It was a lazy, slow rotation. One turn every few million years. Then gravity got to work. The cloud began to collapse. Slowly, over millions of years, its particles rushed toward the center. Its radius shrank by thousands, then by millions of times. Just like a figure skater who pulls her arms in and suddenly spins faster, the collapsing cloud had to rotate more and more rapidly to conserve its original angular momentum. Slow circling turned into a furious vortex. As the cloud contracted, it flattened from a shapeless sphere into a thin, fast-spinning disk, the protoplanetary disk. At its center, where matter packed together most tightly, pressure and temperature rose until nuclear fusion ignited, and a star came to life, our Sun. From the remaining dust and gas in that rotating disk, planets clumped together, inheriting the common spin. Earth, Mars, Jupiter, they still turn today because they're the children of that original gravity-compressed whirl. Their rotation is the echo of the solar system's birth. Behind that law lies an even deeper truth about the universe's structure. At the beginning of the 20th century, Emmy Noether, the greatest female mathematician in history, proved something astonishing. She showed that every conservation law in physics maps directly to a fundamental symmetry of the world. Take angular momentum. It's what governs a figure skater's spin and what keeps galaxies turning. Its conservation follows from a single fact: space is isotropic. In other words, the universe has no preferred direction. The laws of physics behave the same whether you look left, right, up, or down. Because of that exact, inviolable symmetry, rotation can't simply appear or disappear. It must be conserved. Rotation is built into the structure of reality itself. When gravity squeezes an object, it makes it spin faster. Slow drift turns into rapid rotation. That idea feels universal. It feels nearly absolute. But follow that logic to the end and it opens startling questions. Is there a limit to how fast something can rotate? What if you compressed an object the size of a star down to the size of a city? Could it spin so fast that its surface moves nearly at the speed of light? And the opposite question is just as strange. Is there a cosmic break? Something that can slow a planet's spin, stretching its day from hours into many hours and then into days? Most puzzling of all, if this rule is so fundamental, why do galaxies show us the opposite? Stars at their edges race around at such high speeds they ought to have been flung into intergalactic space long ago. What invisible shackles hold them in orbit, apparently defying everything we understand about gravity and rotation? The law of conservation of angular momentum feels absolute. When matter contracts, it spins faster. You see it in the motion of planets and in the birth of stars. But every rule has a limit. Extreme cases that push its logic toward absurdity. Far out in deep space, objects exist that drive this law to its logical, terrifying, unimaginable extreme. They are cosmic spinning tops, turning so violently that the fabric of space-time around them begins to warp. They are the dead hearts of giant stars, squeezed by gravity into a point of unfathomable density. Neutron stars, or as they're also called, pulsars. To make an object like this, nature stages the most spectacular show in the universe. A supernova. A star many times more massive than our sun runs out of fuel. For millions of years, thermonuclear fusion held gravity in check. Then gravity finally wins. In a fraction of a second, the star's outer layers rush inward at tens of thousands of kilometers per second. A colossal explosion tears outward, briefly outshining an entire galaxy. But the real drama happens in the core. Gravity crushes it with such brutal force that protons and electrons are forced together, turning into a solid sphere of neutrons. A mass greater than our sun compresses into a sphere only 20 to 30 kilometers across, roughly the size of a mid-sized city. A single teaspoon of that material would weigh billions of tons on Earth. And here a familiar law comes into play. The giant star had been rotating very slowly, one rotation every few weeks. Now its radius has shrunk by a factor of tens of thousands. To conserve angular momentum, its rotation rate had to skyrocket. The result of this process defies the imagination. The fastest pulsars we know spin as fast as 716 times per second. Not per hour, not per minute, per second. While you blink, an object about the size of a city, yet more massive than the sun, can complete nearly 1,000 rotations. That's a rotation rate at which helicopter blades look motionless. At the equator, the surface sweeps around at roughly a quarter of the speed of light, about 75,000 kilometers per second. The centrifugal force there is so enormous that, if gravity didn't hold it together, gravity rivaled only by black holes, the star would be shredded down to atoms in an instant. Pulsars are the triumph of the law of conservation of angular momentum, its most brutal and awe-inspiring expression. They set the ultimate limit on how fast anything can spin in our universe. If there can be a cosmic accelerator, must there also be a cosmic brake? If you can spin something up to extreme speeds, can you slow it down? Yes, and it's happening right now, overhead. Our planet, Earth, is gradually losing its spin. The culprit is the moon. It doesn't just light the night sky, the moon acts like a vast gravitational brake, stealing Earth's rotational energy over billions of years. This isn't a sudden event. It's a slow, majestic dance between two celestial bodies unfolding across geologic epochs. The way this braking works is elegant in its simplicity. The moon's gravity pulls everything on Earth toward it, but the effect shows up most strongly on the oceans. Water beneath the moon rises, forming a tidal bulge. Another bulge forms on the opposite side of the planet. If Earth didn't rotate, those two bulges would sit directly under the moon. But Earth spins faster than the moon orbits it. That spin drags the bulges forward, so they sit slightly ahead of the moon in its path. Now the moon's gravity tugs on those forward-leaning bulges, trying to pull them back into line. This constant gravitational tug-of-war. That's tidal friction. The ocean floor constantly grinds against those enormous masses of water the moon won't release. Spread across the whole planet, that friction acts like a massive brake pad, steadily slowing Earth's rotation. You can measure the consequences. They're unmistakable. Each century, a day on Earth lengthens by roughly 2 milliseconds. That sounds negligible, but 400 million years ago, in the age of the dinosaurs, a day lasted only 22 hours, and in the distant future, days will grow even longer. So where does that stolen rotational energy go? Energy can't simply vanish. Angular momentum has to go somewhere. We pass it to the moon. When the moon receives that energetic shove, it doesn't spin faster. Instead, it climbs into a higher orbit. Every year, our satellite moves away from us by 3 8/10 centimeters. We measure that with astonishing precision, firing lasers at the corner cube reflectors the Apollo astronauts left on the lunar surface. This isn't theory. We confirm it night after night. The dance continues. Earth slows and the moon drifts outward. We have laws that neatly describe how things spin and how they slow down. From a figure skater to a pulsar, from the Earth to the moon. The same principles apply. It looks like we've found the key to cosmic mechanics, so, feeling confident, we scale up one level, to galaxies. Vast islands of stars turning in the silent void. And here, at the largest scale, our tidy picture collapses, instantly. The laws that worked flawlessly suddenly break down. Galaxies don't rotate the way those laws predict. How can that be? In the 1970s, astronomer Vera Rubin was doing work that looked routine at first glance. She was measuring how fast stars moved in the nearby Andromeda galaxy. The scientific community, largely made up of men, greeted her work with a kind of condescending skepticism. Rubin didn't argue. She was meticulous and relentless. She measured exactly what she saw. The expectation was simple, rooted in Newton's laws. Stars near a galaxy's center, where most of the mass sits, should orbit fast. Stars on the outskirts, where there's far less matter, should orbit slowly, like planets at the edge of the solar system. But her data wasn't just odd, it was impossible. The stars at the edges of galaxies were moving at the same staggering speeds as the stars in the center. That directly contradicted everything we thought we knew about gravity. Think of a carousel. Kids on the rim have to hold on far harder than kids near the hub. Spin it too fast and the children on the outside get flung off. A galaxy behaves the same way. By the math, the visible mass, stars, gas, dust, was nowhere near enough to keep those outer stars in orbit. Their gravitational grip wasn't strong enough. Those stars should have escaped billions of years ago and drifted into intergalactic space. But they didn't. The galaxy stayed intact. That left two possibilities. Either our laws of gravity were wrong, or something else was holding galaxies together. Something massive. Something invisible. Vera Rubin's discovery gave us the first undeniable proof that something we now call dark matter exists. It's not empty space. It's a mysterious substance that doesn't emit, absorb, or reflect light. It stays invisible to our telescopes. We know it only by its gravity. And there's an astonishing amount of it. Calculations show that all the ordinary matter we know, stars, planets, you and me, makes up only about 5% of the universe's mass. Roughly 27% is dark matter, The rest is an even stranger component called dark energy. We live in a universe that is 95% invisible and largely unknown to us. Dark matter acts like an invisible gravitational skeleton, the framework galaxies hang on. It supplies extra pull, the unseen bonds that keep stars at the edges from flying off. Its existence explained why galaxies don't simply fall apart. But that discovery, while it solved one mystery, only pointed to another. Dark matter explained how fast galaxies spin. It didn't explain their shapes. Why do so many galaxies wear those elegant spiral arms? If a galaxy were just a loose cloud of stars orbiting a center, its arms would wind tighter and tighter over time. They'd wrap into the core and fade, turning a spiral into a featureless disk. But they don't. That pushes us onto a different question and into the idea of density waves. In that picture, spiral arms aren't fixed structures. They're more like cosmic traffic jams, regions where stars slow down and crowd together as they pass through. Even so, that still leaves the most basic, almost childlike question unanswered. Why do spiral arms exist at all? We've figured out how rotation speeds up as things contract. We've watched how tidal forces slow it down. We even discovered invisible matter, dark matter, that controls rotation on galactic scales. But all of that only explains how motion gets stronger or weaker. It doesn't explain where the original primordial kick came from in an almost perfectly uniform early universe. What nudged the very first gas cloud or even the tiniest twitch and set off this enormous chain reaction? To find that answer, we have to leave the scale of galaxies behind and descend to the most fundamental level of reality, a realm governed by strange, counterintuitive laws. Because it turns out, rotation isn't just something objects do, it's part of what they are. So why can't you push your hand through a wall? The answer isn't in the table's density, not in the strength of interatomic bonds. It's hidden in the void. Every bit of matter that makes up your world, from the air you breathe to the chair you're sitting in, is 99.9% vacuum. Atoms, those tiny bricks of reality, are mostly nothing. If an atom were the size of a stadium, its nucleus would be a pea at center field. The electrons would be specks of dust swirling somewhere up in the stands. Between them, empty space. Your hand is mostly empty. The wall is mostly empty. So why can't one empty space pass through another? Because we've been looking at the wrong scale. We studied planets and galaxies, but the root cause of motion, of structure, of solidity hides down there, in the subatomic void, in a realm where familiar logic breaks down and reality behaves like a magician gone mad. At the deepest level, every particle of matter carries an intrinsic property, as basic as mass or electric charge. Physicists call it spin. It's about the worst name they could have picked. The word makes you picture a tiny ball turning on its axis, a microscopic planet. But that's not what it is. Electron spin isn't literal rotation. It's an internal quantum form of angular momentum. It's not something the particle does. It's what the particle is. Think of it as the particle's quantum passport, a fundamental trait that governs how it interacts with the world. And unlike a figure skater who can spin faster or slower at will, a particle's spin only comes in fixed, discrete values. It's quantized, either up or down. No middle ground, not a choice, a law. That strange claim sounded like a pure mathematical abstraction, until two German physicists, Otto Stern and Walter Gerlach, decided to test it in 1922. Their experiment was a study in elegant simplicity. Imagine a lab in Frankfurt. The air smelled of ozone and the cheap cigarettes Stern chain-smoked. Their apparatus was basically a furnace that vaporized silver, producing a glowing beam of atoms. They aimed that beam through a strong, non-uniform magnetic field. Think of it as a quantum shooting range. Atoms as bullets, the magnet as the sorter. Classical physics predicted an obvious outcome. Each atom would point in a random direction, so the detector should have shown a single blurred vertical band, a continuous smear of all possible orientations. Stern and Gerlach switched on the apparatus. They waited for hours. Then they pulled out the detector plate. There was no blurred stripe. Instead, two sharp, separate spots. Two. No more, no less. The atoms couldn't pick just any direction. Reality forced a binary choice. Spin up or spin down. That was the first direct visual proof that the quantum world obeys its own digital, not analog, laws. The paradox deepens when we insist that spin comes from physical rotation. An electron is a point particle. It has no measurable size. Even if we granted a tiny finite radius, its surface would have to rotate at speeds far beyond the speed of light to account for the observed spin. That can't happen. It would violate the universe's most fundamental limit, the one Einstein put in place. We reach a logical dead end that forces an uncomfortable conclusion. Spin is a purely quantum mechanical property. It has no analog in our everyday macroscopic world. It's a fundamental rule at the deepest level of reality. And that rule, it turns out, carries far-reaching consequences for everything that exists. In 1925, another brilliant physicist, Austrian Wolfgang Pauli, turned the idea of spin into a principle. Known as the Pauli exclusion principle, it sounds deceptively simple. Two identical fermions, the particles that make up all matter, electrons for example, cannot occupy the same quantum state at the same time. Think of it as a cosmic law of individuality. Imagine a hotel with an infinite number of rooms. Each room represents a distinct quantum state, a particular energy level, an orbital, and a spin. When an electron checks in, it takes one of the rooms. When a second electron arrives, it can take that same room, only if its spin points the opposite way, up and down, like two different beds in the same suite. But when a third electron shows up, the room is already full. It can't go in. It has to hunt for another free room on a higher energy floor. No exceptions. That very ban, the quantum no vacancies, is the answer to why your hand doesn't pass through a table. As the atoms in your hand move toward the atoms in the table, their electron clouds begin to overlap. The electrons in your hand try to occupy energy levels already held by the table's electrons. The Pauli exclusion principle steps in like an immovable wall. It forbids it. It says, this quantum state is already taken. Find another one. For your electrons to share those same states, the table's electrons would have to disappear. They don't. So a colossal repulsive force builds up. The force we perceive as solidity. Solidity isn't a property of the material. It's a macroscopic manifestation of a quantum law that prevents particles from losing their individuality. Your hand and the table are 99.9% empty space. But it's a programmed emptiness, one that won't tolerate intrusions. But that's only the tip of the iceberg. That same quantum rule actually shapes the world around us. Chemistry exists because of the Pauli exclusion principle. Without it, every electron in an atom would simply fall into the lowest energy level, hugging the nucleus. Atoms would be tiny and chemically dead. Instead, the Pauli principle forces electrons to spread into higher and higher energy shells, building the layered structure we read in the periodic table. Those outer electrons, pushed to the edges by a quantum law, take part in reactions, form bonds, and build molecules. Without Pauli, there would be no water, no oxygen, no carbon, no complex organic molecules, no DNA, no life. All the astonishing variety and complexity of our world springs from a single simple rule. No two particles can occupy the same quantum state in the same place. This law doesn't stop at atoms. It reaches all the way to the stars. When a star like our Sun runs out of nuclear fuel, it can no longer hold itself up and begins to collapse under its own gravity. Gravity pushes to cram the star's mass into an ever smaller volume, ultimately toward a point. But the Pauli exclusion principle stands in its path. Electrons in the core get packed so tightly that every low-energy quantum state is filled. They become what physicists call a degenerate electron gas. Gravity squeezes harder, but the electrons resist. Not because of electrical repulsion, but because quantum rules forbid them from sharing the same state. That degeneracy pressure, like a purely quantum effect, halts the collapse and prevents the star from being crushed. The result is a white dwarf, an object about the size of Earth with roughly the mass of the Sun, whose stability comes from the same law that makes your table solid. The picture falls into place. We began with the illusion of stillness. We end up at a level of reality where stillness is impossible. We looked for the source of rotation in space and found it inside every particle. Saw a vast cloud of interstellar gas slowly collapsing, begins to spin. Why? Tiny random motions of its particles, each carrying intrinsic spin, add up into a net angular momentum. That angular momentum stays with the cloud. As it contracts, conservation of angular momentum speeds the spin, and the collapse gives rise to stars and planets. Planets rotate. Stars rotate. Dark matter's invisible scaffold holds galaxies in rotation. It's a vast chain reaction, not kicked off by an outside shove, but driven by an internal property of matter. Rotation didn't come from outside the universe. Matter wove it into the universe's fabric from the very first moment. And now we come back to the very first, almost childlike question. Why does everything spin? The answer is simple and startlingly deep. Everything spins because, at the most fundamental level, reality is made of particles for which rotation isn't an action, it's identity. The same rule that keeps your hand from passing through a wall is the rule that lights stars and writes the code of life. The universe isn't a static backdrop. It's a continuous process, like a never-ending dance of energy and matter, choreographed by elegant quantum laws. The illusion of stillness we began with falls away. In its place comes a clear truth. You, your body, this planet, your galaxy, all of it is part of a single, all-pervading, eternal motion. There is no rest. There is only the dance.